Dear students, welcome to my YouTube channel PCM Academy and myself Prasenjit Mallik, M.sc in Physics. We are in a lecture series for IIT JAM Mathematical Physics, and we have discussed in the last class eigenvalues and eigenvectors. One particular problem that was 2 by 2 matrix, and we have found out the eigenvalues and eigenvectors corresponding to this matrix, that is 2 by 2 matrix. Now we will be going to the next level of problems involving eigenvalues and eigenvectors, that is involving 3 by 3 matrix. So let us solve this problem, and before solving this problem, let me tell you that if you are new in this channel, then please subscribe my channel and hit the bell icon also, so that you can get the further notifications. If you are preparing yourself for these kinds of competitive exams based on physics like IIT JAM, Jest, neet, or any other M.sc entrance, then this channel will be very helpful for you. So let me discuss this problem. So we have to find out the eigenvalues and the eigenvectors corresponding to this matrix A. Let us find out first the eigenvalues, and for eigenvalues we have to solve the equation, the characteristics equation, that is A minus lambda I is equal to 0. Okay, so what will be this? It will be 2 minus lambda 0 0 0 minus lambda 1 0 1 and minus lambda, and that will be equal to 0. So now if you solve it, you will get this 2 minus lambda into lambda square minus 1 equal to 0. So from here you will get 2 minus lambda is equal to 0, that is lambda is equal to 2, and from here you will get lambda square minus 1 is equal to 0, so lambda is equal to plus minus 1. So we have three eigenvalues, one is minus 1, another is plus 1, and another is 2. So now what we have to do, we have to find out the orthonormal eigenvectors corresponding to minus 1, 1 and 2. Okay, so let us first find out for lambda is equal to minus 1. Okay, so for lambda is equal to minus 1, let us take the corresponding eigenvector x1, and that will be just x1, x2 and x3. Now what will be x1, x2, x3? It will give you from the equation A x1 is equal to lambda x1, because if lambda is the eigenvalues corresponding to x1, then it will satisfy this equation. So now if you put the value of A, so what is A? A is same as you have used before, that 2 0 0 0 0 1 and 0 1 0 into x1, that is obviously x1, x2 and x3 is equal to lambda is nothing but minus 1, and this is again x1, x2 and x3. Now if you multiply these two, you will get just 2x1, and from here you will get x3, and from here you will get x2, and that will be equal to minus x1, minus x2 and minus x3. So if you compare these two, you will get just from here you will get 2x1 is equal to minus x1, that means 3x1 is equal to 0, that means x1 is equal to 0, and from here you can see that x3 is equal to minus x2 and x2 is equal to minus x3. So what will be your eigenvector x1? So what will be the value of x1, x2, x3? So your x1 will be just, you can see from here that your x1 will be just 0, and here from here you can see that x3 is equal to minus x2 and x2 is equal to minus x3. So if you take this as x2, then this will be your minus x2. Okay, so and that will be your x1, and if you want to write it in this way, you can write it in this way also. If you take a proportional to constant here, so we like to write it in this way directly. that x1 is equal to, we have a proportionality constant k here, and for here we can write 0, and instead of x2 you can write 1, and instead of minus x2 you can write minus 1. So this x2 and x3 will get this kinds of value such that this will be x2 and this will be minus x2. That means this is 1, this is minus 1. But this is not unique, because it can be multiple of any k. Okay, so we have to use a proportionality constant k, that will be x1 is equal to k, 0, 1 and minus 1. Now if you want to find out the normalized eigenvector, then obviously you have to find out the value of k by using the normalized condition. And what is the normalized condition? Is very simple. If you take x1 transpose x1, and that will be equal to identity. So what will be your x1 transpose? That will be just k, 0, 1, minus 1, and this x1 is again k, 0, 1 and minus 1, and that will be equal to identity. So you can see from here that your k square into what we have, 1 plus 1, that is 2, equal to 1. So your k square will be 1 by 2. So your k will be 1 by root 2. So this is your will be normalized constant, normalization constant. So your x1 will be 1 upon root 2, 0, 1, minus 1. So this will be your eigenvector. Now let me tell you one thing, that you can find out directly this normalization constants. Instead using this equation again and again, you can use in short that you have to take the square root of these elements. That will be, you can say 0 square plus 1 square plus minus 1 square, that will be 2. And if you take the root of this, square root of this, that means you have to just take 0 square plus 1 square plus minus 1 whole square. That will be your root. And you have to just reciprocal of this root. You have to take the reciprocal of this. So if you take the square root of this element, and then if you take the reciprocal of this, then you will get always the normalization constant. Okay, so you can use this equation also. If you want to find out the normalized constant, then you should use this equation, but you can use it directly by using this trick. Okay, so this is the eigenvector corresponding to the lambda 1. Now for lambda is equal to minus 1. Now for lambda is equal to 1 and lambda is equal to 2, what will be our eigenvector? Let me see. Okay, now let us take for lambda is equal to 1. Now what will be in this case? Let us take this is x2, so it will be ax2 is equal to lambda x2. Now it will be again 2, 0, 0, 0, 0, 1, 0, 1, 0, and x2 is again x1, x2, x2 and x3. That is equal to just 1 into x1, x2, x3. Okay, so now what will be the thing? This will be your 2x1 equal to x1. This will be same, and now your x2 will be x3 and your x3 will be x2. Okay, so if you take x1 as 0, then x2 will be 1 and x3 can be 1. So your eigenvector will be this. So this is your now x2. This is your x2. Now what will be again the normalization constant? K will be again root over 1 square plus 1 square, that is 1 upon root 2. So x2 will be again 1 upon root 2, 0, 1. Okay, now let us find out for lambda is equal to 2. Okay, so what will be for lambda is equal to 2? So here again we have to use that ax3 is equal to lambda x3. So here a is nothing but again 2, 0, 0, 0, 0, 1 and 0, 1, 0. Okay, and x3 let us take again x1, x2, x3, and for lambda it will be 2. So 2 into x1, x2, x3. Okay, now Again, if you multiply this, you will get 2x1 is equal to 2x1. You will get just x3 is equal to 2x2, and you will get x2 is equal to 2x3. Now you can see from here that this is 2x1 is equal to 2x1, and x3 is equal to x2, and x2 is equal to 2x3. This will hold if we take x2 and x3 as 0, and x1 can take any value. So let us take that k 1, 0 and 0. So this will be your x3, and your normalized constant here is 1. So your x3 will be k 1, 0, 0. Okay. So what we have got? We have got corresponding to lambda is equal to minus 1. We have x1, that is nothing but 1 upon root 2. There is nothing but 1 upon root 2. 1 upon root 2. We have just 0, 1 and minus 1, and then we have got for lambda is equal to 1, x2 is equal to 1 upon root 2, 0, 1, 1, and then we have for lambda is equal to 2, we have x3, and that is again 1, 0, 0. Okay, so this is your eigenvector x1, x2, x3, and you can check that this is orthonormal to each other. They are orthonormal to each other. Okay, so this is how we can find out the eigenvector corresponding to the eigenvalue for 3 by 3 matrix also. Now let us take one more example so that you can understand. So here the eigenvalues and orthonormal eigenvector again we have to find out. So here A is equal to this. So first what you have to find out? You have to find out just A minus lambda I to 0. So again what you will get from here is 1 minus lambda 0, 0, 0 minus lambda 1, 0, 1 and minus lambda. Okay, so this will equal to 0. Now if we solve it, you will get just 1 minus lambda into lambda square minus 1 equal to 0. Now from here you will get, just let me analyze this result, it's very important. From here you will get just lambda is equal to 1, but from here you will get lambda is equal to minus 1 and plus 1. So now what you have in your hand, lambda is equal to 1 and 1 and lambda is equal to minus 1. So you have two same eigenvalues. So these eigenvalues are called degenerate eigenvalues. Degenerate. And here this lambda is equal to minus 1 is non-degenerate. This is non-degenerate. Okay. Now we have to find out the eigenvector corresponding to this. So first let us find out for lambda is equal to minus 1. Okay. So for lambda is equal to minus 1, let us take the eigenvector is x1. So what we will get, ax1 is equal to lambda x1. So again here a1 0 0 0 0 1 and 0 1 0 into x1. Let us take it as x1 x2 x3 again, that will be equal to minus 1 into x1 x2 x3. Now again if you compare, you can see your x1 will be just minus x1, that means 2x1 is equal to 0. So your x1 will be 0, and you can see from here your x3 will be minus x2, and your x3 will be minus x2, and your x2 will be x3. x2 will be x3. So again what you will get? You will get that x1 as 0, 1 and minus 1. Okay, so if you take x2 as plus 1, then your x3 will be minus 1 multiplied by k, and you will get from here that 1 by root 2, 0, 1 and minus 1, and this is your x1. This is your x1. Okay, this is your x1. So this is the eigenvector corresponding to lambda is equal to minus 1. But the interesting thing is that we have to find out lambda is equal to 1 and 1. But you can't say that for lambda is equal to 1 and 1 we will get the same eigenvector, because we have to find out the orthonormal eigenvector. So we have to find out two eigenvectors such that orthonormal to each other. Okay, so let us first find out for lambda is equal to 1. So if you take here for lambda is equal to plus 1, so here will be plus 1, so this will be plus 1, this will be also plus. So what you will get from here, you can see your x1 will be equal to x1, so you can't say that your x1 will be 0, it will take any value. And here also you can see x3 is equal to x2 and x2 equal to x3. So what we have to take here, the x2 as, so you can take x2 as 1, we have to take here x2 as 1, 0 and 0, we can take this, because your x1 can take any value and we can take x3 and x2 as 0 and 0, so that will satisfy x3 is equal to x2 and x2 is equal to x3. You can take other way also, but let us take in such a way that we can easily find out the orthonormal eigenvector for this x2. The normalized constant is also 1, so we have to find out now x3. So we have to find out x3 such that x3 is orthonormal to x2. So if x2 is orthonormal to x2, or if you can say that if x3 is orthogonal to x2, then we can take the normalized constant, so that will be orthonormal. So first let us find out the orthogonal vector. Then if you normalize it, you will get the orthonormal eigenvector also. So if x3, you can take, let us take x3 as just x1, x2, x3 again. x1, x2, x3 again. So how you can find out this x3? Okay. So if x3 is orthogonal to x2, then obviously this equation will satisfy. x2 transpose x3 is equal to 0. This equation will satisfy. So what is our x2? We have x2 as 1, 0, 0. So x2 transpose will be just 1, 0, 0 in this way. And x3, let us take as x1, x2 and x3. So from here you can say your x1, x2, x3 is this, and this is 1, 0, 0. So from here you can see your x1 will be 0. Your x1 will be 0. Okay. So if x1 is equal to 0, and from here you can see your x2 and x3 are equal. So let us take x2 and x3 as 1. So if you take x2 and x3 as 1 and x1 is equal to 0, then that will give you the orthogonal eigenvector. So your x3 will be just 0, 1 and 1. And if you want to normalize it, you will have just x3 is equal to 1 upon root 2, 0, 1, 1, 0. So this is your orthonormal eigenvector. So what we have first, for corresponding to lambda is equal to -1, for lambda is equal to -1, we have x1, and that was obviously 1 upon root 2, 0, 1, -1, something like this, I think. Yes. And then if you take as lambda is equal to 1, then your x2 will be just, let's take 1, 0, 0, 1, 0, 0. And if you take lambda is equal to 1 again, then we can write x3 as 1 upon root 2, 0, 1. So what you can see from here, that for different eigenvector you have same eigenvalue. You have same eigenvalue. For different eigenvector you have same eigenvalue. So this is known as degenerate case. So we will see this thing in more detail in quantum mechanics, that how this can be happen. Okay, but here mathematically you can see for the same eigenvalue we can get different eigenvector, and which are also orthonormal to each other. So this is most important. So these vectors are orthonormal to each other. These are not unique actually. These are not unique. They are not unique. But we have a set of vector x1, x2, x3 such that they are orthonormal to each other. Okay. So this is how you can find out the eigenvalues and corresponding to that eigenvalues, the different kinds of eigenvectors that are asked. Okay. Now let me solve another more example that is based on CH theorem, that is Cayley-Hamilton theorem. So how you can find out A inverse by using this kinds of this theorem, this Cayley-Hamilton theorem. In the first class I have told you that you can find out A inverse by using the characteristics equation. But how you can find out, let us tell you from here. So let us first find out the characteristic equation from here, that is nothing but mod a minus lambda I is equal to 0, and that will be what? That will be just 1 minus lambda 3 4 and 2 minus lambda equal to 0. So that will obviously be 1 minus lambda into 2 minus lambda minus 12 equal to 0. So that is what you can write over here, that is 2 minus lambda minus 2 lambda plus lambda square plus 12 equal to 0. So that is nothing but lambda square minus 3 lambda plus 14 equal to 0. Let me check. I don't believe myself, my calculation. Let me check. So 1 minus lambda 2. Okay. Okay. So lambda square minus 3 lambda plus 14 equal to 0. But the lambda square minus 3 lambda minus 10. Why? Okay. So they use 5 here. Okay. So this is okay. So 1 minus lambda and 2 minus lambda. So that will be 2 minus lambda minus 2 lambda square. This is minus 12. Sorry. So minus 12 plus 2. So this will be minus 10. So we have lambda square minus 3 lambda minus 10 equal to 0. Okay. So this is our characteristic equation. Lambda square minus 3 lambda minus 10 is equal to 0. So this is our characteristic equation. Okay. Now, according to CH theorem, we can use a instead of lambda. So this is f of lambda is equal to 0. And according to CH theorem, that f of a will also be 0. That means from here we can write a square minus 3a minus 10 will be 0. So this can be write in this way, that is a square minus 3a minus 10I is equal to 0 actually. Now we can write for I as a inverse. Okay. So what we have? We have a square minus 3a minus 10I equal to 0. So we can write a square minus 3a minus 10. Instead of I, we can write that a inverse equal to 0. So what will be your 10a inverse? Will be a square minus 3a. Now if you want to find out 10a inverse, that will be a minus 3i. Now your a inverse will be 1 upon 10 into a minus 3i. Now you can see this will be very easy. So what will be your a inverse? 1 by 10. And now what is a? A is 1342 1342. Okay, this is your matrix. Minus 3 into I, that means 2 by 2. It will be 1 0 and 0 1. So you can find out from here that 1 by 10 into your 1 minus 3, that will be minus 2. Then 3 minus 0, so that will be 3. Then 4 minus 0 will be 4. Then 2 minus 3, that will be minus 1. So this is your a inverse. This is your a inverse finally. So if you want, you can take this 10 over here. So you can write it in this way also. Minus 2 by 10, that will be minus 1 by 5, 3 by 10, 4 by 10, that will be again 2 by 5 and minus 1. So you can find out this a inverse by using this, only by using subtracting or the addition of matrix. By using subtraction and addition of matrix, you don't need to do the multiplication. So this is why the CH theorem is very useful when you want to find out the a inverse. Otherwise you can find out a inverse by using this, that is adjoint a. This is also, you can, by using this formula you can find out, but this is easiest process. The calculation will be little less. Okay. So these are our many problems for this class. So you have to practice more and more problems so that your calculation will be more simple. Okay. So you can calculate easily. So in the next class we will discuss about some different kinds of matrices. So I have discussed this matrix chapter in different way, because I have discussed first eigenvalues eigenvector, because questions basically asked from here. So that's why I have discussed this thing first. Now we will discuss about the different kinds of matrices also. Okay.